Friends, welcome back. In this video, we will discuss about VPC operations in detail and also configure VPC on a pair of Nexus switches in a lab setup. And we will also configure VPC port channel towards a couple of end stations and make sure that those end stations can reach each other over the uplinks connected to the VPC peers. So friends, like we previously discussed, VPC is made up of two identical physical boxes, also called the VPC peers. And these VPC peers must have the same model number, same modules, line cards, etc. As there is a consistency check that runs behind the scene over a protocol called Cisco Fabric Services over Ethernet or CFSoE. It is a custom protocol specifically for VPC to synchronize the MAC address table, the ARP cache, etc. And when these VPC peers form a peering over this protocol, at that stage, the VPC peers exchange their physical parameters as if they have incompatible line cards. They cannot be used to create a port channel towards the downstream device. So from a configuration point of view, there is no configuration required for these consistency checks. So the VPC process does it automatically as soon as we create the VPC peer link. So as soon as the VPC peer link comes up between the VPC peers, they exchange these parameters. So friends, this is the physical topology that we will use for implementing VPC in this video. So we have a pair of Nexus switches and they are connected to each other on two physical links for VPC peer link. So we are using Ethernet 1/8 and Ethernet 1/9 to form the VPC peer link. They will be configured in port channel 1 on both peer 1 and peer 2. And they're also configured or connected across a third link, which is the management link for bringing up the VPC peer keep alive link. So the first step in configuring VPC in our topology is to enable the feature. So we will go to the two peers, peer 1 and peer 2, and enable feature VPC in the global config mode. So it's a feature VPC on peer 1 and enable feature LACP to negotiate port channel on the link towards the servers. We don't necessarily have to run LACP, but we should do it if we could. We could also do static channeling as the last option only if the downstream device does not support LACP. So we enabled feature VPC and feature LACP on peer 1. So now we'll do the same on peer 2, feature VPC and feature LACP. So the next thing that happens is that the VPC peers form what we call as a VPC domain. So we assign an identifier to the VPC domain that is shared between the two peers, and this domain ID is used to generate the shared link aggregation ID or LACP ID. This link aggregation ID or lag ID is used to trick the downstream device into thinking that the upstream device is one physical device instead of two physical switches. So let's say if we define VPC domain 1 on peer 1 and VPC domain 1 on peer 2, and using this domain ID, the two VPC peers will generate a shared lag ID or link aggregation ID. So let's say the shared link aggregation ID is a value of 1. This ID will be sent to the downstream device, in our case server 1, by both peer 1 and peer 2 in the LSCP negotiation. With that, the server 1 will think that it's connected to the same upstream device instead of two physical devices. So when we negotiate the port channel from the peer switches towards the server, we have LSCP going out this direction and we have LSCP going out from peer 2 towards the server. We need to make sure that the identifier that is sent from both peer 1 and peer 2 they have the same value. So the server 1 now thinks that it has a point-to-point connectivity to the same upstream device. This basically means that the VPC domain ID on both the devices or on both the VPC peers must be the same. The VPC domain ID is also used to generate the VPC system MAC address. The first 5 bytes of the VPC system MAC address are a fixed Cisco reserved value, which is the value you see on the screen now. But the last byte of the MAC address is the hexadecimal equivalent of the VPC domain ID that we configure. So in our lab topology, the VPC system MAC address that we should see is the value that you see on the screen highlighted, ending with 01, as 01 is the hexadecimal representation of decimal value 1. The next thing that we need to make sure is that the VPC peers are able to track reachability between each other. They are going to do this over a link called the VPC peer keep alive, which is a UDP ping going between the peers over UDP port 3200. And when it comes to VPC peer keep alive, we have multiple options. We can use the management port to carry the pings out of band. We can use routed interface like a layer 3 port channel or an SVI. They don't even have to be on the same subnet as long as they can route to each other. And as long as the two peers can ping each other, that's the only requirement for the VPC peer keep alive link. And as far as our lab topology is concerned, we will be using management port 0 to send the UDP pings to each other. We then have the synchronization of the control plane over the peer link. The peer link is a layer 2 port channel, and this is what we use to synchronize the MAC address table back and forth between the two peers. The main objective here is that since we have that physical triangle, and the downstream service point of view, it's going to have one logical team interface, let's say team 1. We will have one IP address, let's say 10.0.0.1. This also means that we have one MAC address, let's say MAC address of A. We need to make sure that both the VPC peers, peer 1 and peer 2, synchronize the MAC address table across the VPC peer link, basically telling each other that if you want to get to MAC address A, we can either go via peer 1 or peer 2 this way. So the server's MAC address should be equally reachable over the VPC member port. So VPC member port is the port channel going down to the end station or whatever the downstream device is, and we match the identifier for that member port between the two VPC peers. And from an implementation point of view, we will see that VPC configuration steps are very sensitive to the order of operation. And the reason being is that there is a dependency order of the VPC that the member port can only come up if the peer link is up, and the peer link can only come up if the peer keep alive is up. This means that when we configure VPC, we must do it in a certain order. So going back to our lab, we have enabled the feature VPC on both peer 1 and peer 2, and we also enabled feature LACP to negotiate port channel on the links towards the servers. So the next step that we'll be doing is to configure a VPC domain ID on both peer 1 and peer 2. And the way we do it is using the command VPC domain, and then we allocate or assign a domain ID from the range 1 to 1000 as you see on the screen. So in our lab, we'll use the VPC domain ID of 1. And likewise, we will do exactly the same thing on VPC peer 2. If we use the context sensitive help, we can see that there are multiple options that we can configure under VPC, but for our lab topology, we'll just use the peer keep alive command to establish the peer keep alive link between peer 1 and peer 2. And like we discussed earlier, we can use the management port out of band, or we can use a routed interface like a layer 3 port channel or an SVI on the VPC peers to establish the VPC peer keep alive. But for our topology, we will use the management port 0 for the peer keep alive link. So on our management port 0, we'll be assigning an IP address. For peer 1, we'll use an IP address of 192.168.0.1/24. And for peer 2, we will use the IP address of 192.168.0.2/24. And we will just make sure that the two devices can ping each other, which they can. We will do the same from peer 2 as well. They do have IP connectivity to each other. And now we will configure the peer keep alive command under VPC domain ID. So going back to peer 1, we will go to VPC domain ID 1. The command to configure peer keep alive is peer keep alive destination, and then we put the destination IP of the VPC peer, which in our case is peer 2 with a management IP of 192.168.0.2. And if we do not specify a VRF here, so if we take the context sensitive help, we see that we can define the source, the VRF, and we have a few other options as well. And if we do not specify a VRF, by default, it will fall back to using the management VRF. So we configure the destination of 192.168.0.2. And likewise, we will configure the VPC peer keep alive on peer 2 as well. So we will go to VPC domain 1 again, peer keep alive, destination 192.168.0.1. So now if we check the VPC state using the command show VPC, we see that the VPC peer keep alive status is peer is alive. And let's say if we do a show VPC peer keep alive command, we see the send status as success, receive status as success, and it was received on management interface 0. The destination is 192.168.0.2. The keep alive interval is 1 second. The timeout is 5 seconds. And there is a hold timeout of another 3 seconds. So if it doesn't receive a keep alive from the remote peer for 5 seconds, it will wait for another 3 seconds before marking the neighbor as down. And it does send the keep alive on management VRF as we see, and it uses UDP port 3200 to send the VPC peer keep alive messages. So next we will establish the VPC peer keep alive connectivity, which will be a layer 2 port channel between the two VPC peers. So VPC peer link is the heart of the system, as that's how they synchronize the MAC address table between the two VPC peers. So if the VPC peer link goes down, there will be a break in the control plane, and they would have to disable the interface going down towards the downstream devices, which we will discuss in the section related to VPC failure scenarios. Also, the VPC peer link has to be a minimum of 2 by 10 gig links, but the size of the peer link is going to be dependent on the aggregate bandwidth that we have going towards the downstream devices in our production network. The more ports we have going downstream towards the servers, firewalls, or any other service layer devices, the larger we should have the VPC peer link because of certain failure scenarios that we will discuss in the upcoming sections. And going back to our lab topology, we will be using interfaces Ethernet 1/8 and 1/9 on both peer 1 and peer 2. And we will be configuring these interfaces as part of peer 1, which will be configured as VPC peer link. So going back to the CLI, so on our VPC peers, if we check the configuration of these interfaces, they should have blank configuration right now. We are under interface Ethernet 1/8 to 9, and we will configure them as part of channel group 1 mode active, and we will do the same on peer 2 as well. So interface Ethernet 1/8 to 9, channel group 1 mode active. And now we will configure interface port channel 1 as the VPC peer link. So the only command that's required to configure the peer link is the VPC peer link command under port channel 1. And likewise, we will do the same on VPC peer 2. So when we configure the VPC peer link under port channel, we used port channel 1 in our example. We got a message saying that please note that spanning tree port type is changed to network port type on VPC peer link. This will enable spanning tree bridge assurance on the VPC peer link, provided the bridge assurance is enabled, which it is by default. With bridge assurance, what happens is that the two VPC peers will ping each other back and forth on a per VLAN basis, which means that if we have a VLAN configured on, let's say, peer 1 and not on peer 2, it will be pruned or removed from the VPC peer link, which means that it cannot forward for that VLAN on the member ports. So we now have the VPC peer link as up. So we see the status change to peer adjacency formed OK. The port channel 1, which is our VPC peer link, is now up. We don't have any VLANs configured, hence we only see active VLAN 1 on port channel 1. So with VPC, there is some changes in regards to how spanning tree behaves. The main change being that if we want to forward a VLAN towards the member ports, that VLAN has to be forwarded across the VPC peer link. So going back to the VPC workflow, we enabled the VPC feature, we defined the VPC domain, we established the VPC peer keep alive connectivity, and then we also established VPC peer link connectivity. And now we will configure or establish the VPC member port connectivity towards the end servers, which are servers 1 and 2 in our topology. So in our lab, we have interface Ethernet 1/1 going towards server 1, 1/2 going towards server 2 from both peer 1 and peer 2. So if we use this show VPC command on the VPC peers, it will show us the VLANs that we are forwarding towards the member ports. So only the VLANs that are matching between the two VPC peers are the ones that go towards the downstream devices. The reason being that the MAC address has to be equal between the VPC peers, and they are synchronizing the control plane to make sure they are forwarding towards the destination correctly. So for this, we created VLAN 10 on peer 1, and we also created VLAN 20 on peer 2. And now if we have a look at the trunk between the VPC peers, we see that VLAN 10 has gone to error disabled state on peer 1, and VLAN 20 has gone to error disabled state on peer 2. So the point being that if we want to forward a VLAN towards the member ports, that VLAN has to be forwarded across the VPC peer link. So now if we create VLAN 20 on peer 1 and VLAN 10 on peer 2, we will see that we no longer see VLANs in error disabled state on trunk. So previously we saw that on peer 2 we had VLAN 20 in error disabled state on port channel 1. Similarly, we had VLAN 10 in error disabled state on peer 1 over port channel 1. But when we configured or created the VLANs on both the peers, we no longer see any VLANs in error disabled state on the VPC peer link, which is PO1. And like we discussed, this is to make sure that both the peers are forwarding towards the destination correctly. And if we check the VPC workflow again, so we have enabled VPC feature on both the peers. We defined the VPC domain ID on both the peers. We established the VPC peer keep alive connectivity. We also established the VPC peer link connectivity. And now we will configure the VPC member ports from the VPC peers towards the end servers. In our topology, we have peer 1 connected to server 1 on its port ETH1/1, and it's connected to server 2 on interface ETH1/2. Likewise, on peer 2, we have Ethernet 1/1 going towards server 1 and Ethernet 1/2 going towards server 2. And for the purpose of this lab, I'm using Nexus 9000V devices to simulate the end servers. So we have server 1 and server 2 connected to both the peers. So we will configure Ethernet 1/1 on both peer 1 and peer 2. So Ethernet 1/1 on peer 1 and Ethernet 1/1 on peer 2, they both go to server 1 and they will be configured as part of port channel 10. So we will go to peer 1, interface ETH 1/1, channel group 10, mode active, no shut. And then we will configure the port channel interface, switch port mode trunk, no shut. Likewise, we will go to peer 2, interface ETH 1/1, channel group 10, mode active, no shut. And now that we have configured the physical interface, we will configure the logical port channel, which is PO10, switch port, mode trunk. Let's do a no shut. And now we will also enter the VPC command under the port channel. Likewise, we go to peer 2 and the command VPC. You can also specify a VPC identifier here. However, if you do not specify a value, the identifier is derived from the port channel number, in this case PO10. So now if we verify the port channel status on both the VPC peers using command show port channel summary, we will see that the port channel 10 connected to its server 1 has come up and it's part of the port channel. Likewise, we go to peer 2, we see interface ETH 1/1 as part of port channel. And if we do a show VPC, we will see that the VPC ID has been derived from the port channel ID, which is PO10. Technically, we could have used different port channel numbers on both the VPC peers as long as the VPC ID is unique or is the same between the VPC peers. But for consistency's sake, it's a good practice to keep the VPC and port channel numbers as the same to keep the setup simple. And we will do the same setup or same configuration for server 2. So we have interface 1/2 on peer 1 and 1/2 on peer 2 connected towards server 2, and we will configure these links as part of port channel 20 on both peer 1 and peer 2. And from server 2's perspective, it will be a standard port channel. So on peer 1, we will go to interface Ethernet 1/2, channel group 20, mode active. Let's do a no shut. And now that we have the physical interface configured, let's configure the logical interface as well. So interface PO20, it will be configured as a switch port mode trunk. Let's do a no shut. And we also enter the keyword VPC. Likewise, on peer 2, we will do exactly the same configuration. So interface Ethernet 1/2, channel group 20, mode active, no shut, interface PO20, switch port mode trunk, and the keyword VPC. If we check the port channel summary on both peer 1 and peer 2 now, we see that both port channels 10 and 20 have come up. And then we also configured an SVI on servers 1 and 2. So we went to server 1 and configured interface VLAN 10 with an IP of 10.10.1.1/24. And we configured interface VLAN 10 on server 2 as well with an IP of 10.10.1.2/24. And if we check the connectivity between the two servers using ping, we see that the two servers can reach each other. And if we check the MAC address table on both peer 1 and peer 2 for VLAN 10, we see that they are learning both the MAC address for servers 1 and 2 on port channels 10 and 20 respectively. So if we check the MAC address for VLAN 10 on server 1, it has a value of OCA1 quad zeros 1B08, and peer 1 and 2, they're learning this MAC address on PO10 as expected. And then server 2 has a MAC address of OCB3 quad zeros 1B08 for VLAN 10. And we should be learning this on port channel 20 on PS1 and 2. So if we check the MAC address table for VLAN 10, we see that MAC address being learned on PO20 on PS1 and 2. So peer 1 learned the MAC address of server 1 in this direction, and it learned the MAC address for server 2 in this direction on PO10 and 20 respectively. Likewise, peer 2 learned the MAC address of server 1 in this direction on PO10 and the MAC address of server 2 in this direction on PO20. So this way, when server 1 pings server 2 and it hashes to this interface, let's say the interface towards peer 1, the traffic will be locally received on peer 1 and it will also be locally forwarded on peer 1. So peer 1 will never receive traffic on its member port and then send that traffic towards its peer over the peer link, and that traffic will never be forwarded to a member port. This is a VPC loop prevention mechanism, and we will discuss this in the upcoming section related to VPC failure scenarios. So in our upcoming sections, we will discuss various failure scenarios related to VPC domain. For example, what happens if the VPC peer link goes down? What happens if the peer keep alive goes down? So we will discuss these scenarios in the next module. So I hope you liked this video, and if you did like the content, please hit the like button, share the video with your colleagues. Any comment you have, good or bad, it's always welcomed. And if you haven't subscribed to my channel yet, please hit that subscribe button. So friends, thank you very much for your time today, and I will see you in the next module. Thanks a lot.